Okay guys, here's the second part of the video instruction for section 1.1.2. This is the solving equations tutorial. So I'm going to go through a couple of examples with you, just kind of laying out the steps and justifying each of the steps for solving these equations. You can get to this resource from our website. This should be on your 1.1.2 materials, and this is your solving equations. These four examples that I'm going to show you should be right there in your packet. Okay, example number one, we have the problem here. That's this given information here, and then they already tell you what the answer is supposed to be, so I'm going to go through the solving process, and we can use this to know that we did it right if our very answer at the end is x equals 3. Now, one of the things that's already different from part 2 and part 1 is we're dealing with equations now. These are equal signs, meaning that everything on the left side is the exact same as everything on the right side. So we got to keep everything balanced in the sense that if I change something on the left, I have to make the exact same change on the right, or these two are no longer equal to each other. We solve equations, which means we're going to get a final answer that looks like a variable equal to a number, as opposed to expressions where all we did was simplify. All right, so now with simplification we used order of operations. Please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, and subtraction. But when it comes to solving, you're almost working backwards, so you want to do the reverse order of operations. So you've got a lot of ways that you could start here, but I like to start from the inside and just try to deal with that a little bit as far as planning. Now, I don't want to start at the inside and start trying to solve that way. I actually do the reverse of that. I start on the outside and I work my way in. So one of the things that I can recognize right away is this minus 9 and this 2, and how I want to get those things away from the x that I ultimately want to isolate. One of the things that you might have heard previous teachers talk about is when you solve, you try to isolate the variable. Well, we've got variables on both sides, so we're trying to figure out which side do we want all the variables on. Well, one of the things that we can do to try to decide that is to get the variables by themselves. So right away, order of operations, please excuse my dear Aunt Sally, addition and subtraction is the last thing. So when solving, that'll be the first things that we get rid of. So in order to get rid of, you're going to do the inverse operation. So the inverse operation is the operation that would undo or get rid of whatever operation you're trying to get rid of. So in this case, this is minus 9 or subtract 9. So I want to do the opposite, which would be add 9. So if I add 9 to both sides, the whole reason I do that is negative 9 plus 9 is 0. And when we talk about getting rid of things or undoing things, making them equal 0, that's what helps us do that. So negative 9 plus 9, those two things add up to 0, so we can say that they cancel out. Therefore, all I'm left with is this 2 times x plus 4. And that's still equal to everything on the right. Now don't forget to make that adjustment with the plus 9 to keep everything balanced. Negative 13 plus 9 is negative 4. So I'm going to continue to work to try to isolate the variable on this side, this x. So I need to get everything away from it. The operation that's taking place with 2 jammed up next to the parentheses is multiplication. So the inverse operation would be division. So now, a lot of you might be thinking, well, those two things don't add up to 0. Correct. But 2 divided by 2 is 1, and 1 times anything is just what you start with. So making things be added to 0 or multiplied by 1 are just like them not changing at all. So when we talk about eliminating addition and subtraction, they add up or subtract to 0, and eliminating multiplication and division, they multiply or divide to 1. So 2 divided by 2 is 1, so we could say that those things cancel. X plus 4 is equal to, and now, important to do here, everybody has to be divided by what's on the bottom. So 6 divided by 2 is 3x, and 4 divided by 2 is negative 2. So now I've got variables on both sides of the equation. Now, you get to kind of choose which way you would like to send the variables to and focus. Some of you always like to have it on the left because that's how our answer looks here, which is fine. I personally like to keep the variables positive. So I look, which side do I have the more x's on? On the left side, I've got 1 x, and on the right side, I've got 3 x's. So I'm going to send everything to the right side. So I'm going to subtract x from both sides as I'm trying to eliminate the x's on the left side. X minus x is 0x. So those two things cancel out, and I'm left with a 4. And 3x minus x leaves me with 2x minus 2. So now I'm going to continue to try to isolate my variable. So everything that's not a variable has got to go to the left side. So how do I get rid of minus 2? Inverse operation, add 2. And I got to make sure I do that to both sides here in order to keep it balanced and equal. Those things cancel out as they go to 0. 2x is equal to 4 plus 2 is 6. Now my last step is to get rid of the multiplication that's taking place here. So how do I get rid of multiplication? I divide. So I'm going to divide both sides by the same thing, 2. 2 divided by 2 is 1, so 1 times x is just x. And 6 divided by 2 is 3. Now, I can use the I can use the properties of equality, and one of the properties of equality is the symmetric properties of equality, which means I could change the order of the equation and it'd still be equal. Meaning 3 equals x is the same thing as x equals 3 according to the symmetric property of equality. So there we have it. We've got the exact same answer as we were supposed to prove, and all of these steps justify what we were doing. If I go back through and use this idea of a 2-column proof, that basically means that everything on the left side that I did, the work, that's kind of my steps that I took, and on the right side I would justify the answers. So what did I do on each step? Well, the first thing that I did over here on the right is I added 9 to both sides, and the next step I divided by 2 to get rid of that 2. Next I subtracted 1x. After that I added 2 to both sides, and finally I divided by 2 in order to get x by itself, and then I use the symmetric property in order to get x to the left and make it identical to the proof statement. So that's one of the ways that we can use justification to kind of prove why x is equal to 3. It's a little bit more drawn out process. You're probably used to just doing the stuff that's on the left, but these things over here on the right side that's using vocabulary, basically answering why I know I was able to solve and get x equal to 3. All right, moving to example 2 now. Go ahead and get all this out of your way. Moving to example 2, it's a little bit different. We don't have any parentheses, but we will have to deal with a few negative symbols here, and we could definitely talk about that. A lot of you might even be trying these examples on your own, which is a good thing, and then you can see what I think about them. All right, so example 2, again, I see that the A is on the left side, so I want to get everybody away from that. Reverse order of operations says that this minus 5's got to go first. So the inverse operation of subtraction is addition. So I'm going to add 5 to both sides. Negative 5 plus 5 is 0, so that's going to leave me with negative 6a, and that's equal to negative 95 plus 5, which is negative 90. Now I'm almost there. I need to get rid of this negative 6. Now that negative 6 jammed up to the a, that means it's multiplication. How do I get rid of multiplication? I divide. So I've got to divide not by the 6, but by negative 6, because I need everything to leave with that in order to make sure that a is by itself. So negative 6 divided by negative 6 is positive 1. So we just have an A there. Now, negative 90 divided by negative 6, you might need a calculator to do that. So you can grab your calculator to make you figure that out. But one of the things that I do want to make sure that you remember is that a negative divided by a negative is indeed a positive. So, without further ado, let's grab our calculator here. And we're taking a look. Negative 90 divided by negative 6 is 15. And now you can see that we don't have to do any more steps because that A and that A equals 5, and they look the exact same thing. So we've proven the right thing. Just going through and justifying my steps for that right side of the two-column proof here. I first added 5 to both sides. Then I divided by 6. And that landed me with my answer. Okay. We'll do this very last exam. We're going to skip over 3 and go to 4 really quickly. One of the interesting things about this problem right here is we call this a proportion, where we have a fraction equals a fraction. So there's a couple of different strategies. One of the neat strategies that you can use that works for this is cross multiplication, meaning you can multiply the bottom of the left side times the top of the right side, and the top of the left side times the bottom of the right side. And what that can do is help you eliminate the fractions, because the fractions, let's be honest, are the major problem in this example. But I want to make sure you understand why we're able to do that. If you think about this in terms of, if I wanted to get rid of divided by 3, I would multiply both sides by 3. So I would multiply this side by 3, and I would multiply this side by 3. And if I wanted to get rid of that divided by 5, I would multiply both sides by 5. Well, okay. Well, if we do that, if you'll notice, on each side, these 3's would cancel because I've got a 3 on the top and 3 on the bottom. And when I divide 3 and 3, I get a 1. And over here, the 5's would cancel because when I do 5 divided by 5, I get a 1. So then all I'm left with is 5 times x plus 2 equals 3 times 2x minus 1. Well, if you look and cross multiply, the 3 would be multiplied by the 2x minus 1. Well, that's the right side of our equation. And the 5 would be multiplied by x plus 2. Well, that's the left side of our equation. So you could see that cross multiplication indeed does work, and it works because of inverse operations, getting rid of the denominators with multiplication. So we could go ahead and distribute here if we'd like. So if you go ahead and distribute on both sides, multiplication times everything inside the parentheses, 5 times x is 5x, 5 times 2 is 10. 3 times 2x is 6x, and 3 times negative 1 is negative 3. Now I can ask myself the question, which side has more x's? The right side does, so I'm going to subtract 5x from both sides. Again, this is a preference of mine. You don't have to do the same thing, but I like to do it because it keeps my variables positive. 5x minus 5x is 0, so those cancel. I'm left with a 10. 6x minus 5x is 1x, or just x. Bring down my minus 3 because that was unchanged. I want to get x by itself, so I've got to get rid of minus 3 by doing the inverse operation. Add 3 to both sides. 13 is equal to x, but I want to rewrite this like the proof statement, so I can use the symmetric property to swap this equation around, because changing the order does not change the equation. All right, again, just one more justification. This step here would be the distributive property. This step here, once I distributed, I subtracted 5x, and then I added 3 to both sides, and finally I used the symmetric property of equality to switch the equation around and make it identical to the proof statement. I hope this was helpful for you, and I hope you could try out those examples now. Good luck.